Anyone want to do questions? Ladies and gentlemen, welcome to the Geological Society of London, and to this, the 9th Society London Lecture of 2017, the title of which is Why Earth Developed into the Crucible of Life and Venus into a Hostile Wasteland. My name is Sarah Day. I'm the science communicator here at the Geological Society, and it's my pleasure to introduce our speaker, Dr. Sami Mikhail. Differences in volcanism on the planets of the inner solar system testify to the dynamic nature of planetary formation and evolution. Earth and Venus are sometimes called sibling planets because of their similar size and composition, but their contrasting volcanology, atmospheric mass, and chemistry, climate, and geomorphology are striking. Venus's atmosphere and surface contain 5 orders of magnitude less water than the Earth, and the average surface temperature is 460 degrees Celsius. Venus is also relatively flat. I did not know that, with only 2% of its surface showing any appreciable topography. That kind of flat, not flat Earth flat. I did stumble on that one. Earth, by contrast, is wet and cold, with orogenic belts and oceanic basins. By combining rock deformation experiments with the chemistry of Venusian and terrestrial atmospheres, we can start to explain Venus's flatness and relative volcanic quiescence, and so begin to see why Earth became the crucible of life and Venus a hostile wasteland. Sami Mikhail lectures in Earth Sciences at the University of St Andrews following 2 years as a Carnegie postdoctoral fellow at the Geophysical Laboratory in Washington, D.C., and postdoctoral positions at Bristol and Edinburgh. He gained his BSc in geology from Kingston University and an MSc from Royal Holloway and Bedford New College, and a PhD from UCL. Ladies and gentlemen, please welcome Sami Mikhail.
I suppose I should have been told to stand right here. Okay. So first of all, thank you all for coming here today. It's a huge honor for me to be here. I've always been a fan of the society and societies in general, and disseminating science beyond the realm of just simply publishing this stuff. Right? Sometimes you want to get together and say to people, hey, I think I'm doing something really cool, and hope that everyone else here thinks, yeah, that was interesting, I enjoyed myself. So my objective here today is to try and I want to achieve 2 things. I want to disseminate results. I want to show you insights that I think I've provided scientifically. And I also want to hopefully entertain you. I hope you'd enjoy this. I hope this is a pleasurable afternoon for us all. So the title is about why Earth developed into the crucible of life. Now, Earth's also the only place we know there is life. So we have an n=1 problem. So if you were to study me and say, how'd you get a job at St Andrews as lecturer? Do you have to go to Kingston like I did, Royal Holloway, then UCL? No. But if you only studied 1 member of staff at St Andrews, you'd have no idea if there's many ways to get a job there or one. So I'm going to focus on Venus. It's a much maligned planet, really, as far as the news goes. Because we either hear about exoplanets or Mars or icy moons. But Venus itself is a wonderfully strange place. Now, this photo here this is a radar image of the surface of Venus, and this is a photo. So Venus has permanent cloud cover, right? It makes the UK look sunny. There's not a single part of Venus that sees the sky. So we have to look at its surface through radar. So it's completely almost obscured by cloud. It's hidden. It's a mystery. It's enigmatic. It's got some interesting properties. So it doesn't have any moons. And a day on Venus, the amount of time it takes for the planet to rotate, is longer than it takes the planet to go around the sun. So on Venus, you'd have calendars made up of years with a day and 0.2 within them. It's also 460 degrees on average at the surface, and because of the nature of its extreme greenhouse atmosphere, there's very little difference in temperature at the equator and the pole. So it's just all hot, which means the convection regimes are slow, wind is about 2 miles an hour, so it's very, very stagnant. It's first observed by Babylonian astronomers, but it's, curiously, almost as big as Earth. It's the most Earth-like thing we've ever seen. So it's distance from the sun, if we measure in astronomical units, whereby 1 is Earth's distance from the sun, Venus is about 0.72. So it's really similar in terms of where it formed during planet formation. It's diameter, its mass is similar to Earth. So if you just considered the rock and the size and the distance from a star, it's Earth. But as we've seen before, Earth is not 460 degrees at the surface. Some parts of Earth, even in the UK, see the sun. Venus is not that. So if we're going to address how Earth became the crucible of life, that's one question. Why did Venus not become a nice, lovely place for life to live? And moving beyond our solar system, so how can we distinguish an Earth from a Venus or a Venus from an Earth, astronomically speaking? So we've set up the Center for Exoplanet Science at St. Andrews, which is a collaborative effort mainly between earth science, astrophysics, and philosophy, exploring how we can explore the solar systems beyond our own, how we can communicate those results. And some of our actual research in what's named STAG, which is our isotope division, we try and figure out how Earth was built. And so the idea is that we're going to solve all the problems in the world, which don't affect anyone. Blue skies. So here's a pitch from the fourth hole. I'm from St. Andrews now, so I have to show some golf, okay? So this is the night sky, and this is the fourth hole. And ever since I was a child, right, I've been obsessed with the night sky whenever I could see it. And it was, you see stars, and then one day you learn that stars are suns. And you think, do they have planets? And you think, well, if they have planets, do they have people? Is someone else looking back at me? And that's the driving force behind why I want to understand Venus. This is the bane of my life in many ways. So this is what gets BBC news articles every single week almost. This determines the temperature of a star, the energy received by a planet, and then this green band is what's known as the habitable zone. And any exoplanet observed in this habitable zone gets a lot of media attention because the argument is you're in the habitable zone, you can support liquid water on the surface. If you can support liquid water, you have a chance of supporting life. But the habitable zone itself is the first thing we're going to tear apart, should we say. We're going to go through it and explain why it's misleading. So this is what it means. This is a phase diagram. So this sort of diagram just shows you, if you picked a point here, you could say, what is the state of H2O? Now this is where Venus sits. This is why Venus gets much less attention. This is in the present. This is where Mars and its atmosphere sit. And so sometimes on Mars we can have water. So my partner has an app for the weather where the Curiosity rover is, because obviously you have an app for the weather where the Curiosity rover is. And in August, we were sitting at home in Scotland. She checked her app, and it was hotter on Mars than it was in Scotland. So Mars can actually get up to about 20 degrees Celsius, but they're also down to minus 173. And then here's Earth. Earth's amazing, right? So this is like a lot high, under the oceans, right? Super high pressures. On top of the mountains, low pressures. Here's the triple point. So this is why we can see, for example, in Scotland, you always have 3 states of water. You have ice, you have a loch, and then you have it raining. And this is all happening at once. And it's incredible. It's amazing. And so this is why the habitable zone gets attention. It's the triple point of water that we're seeking here. So this is why it's called the Goldilocks zone. And I prefer the term Goldilocks zone because it's slightly, more intuitive. It's either too hot, too cold, or just right. So obviously, Earth is in the habitable zone. Venus is not. End of the talk. You can all go home. But I'm not happy with the habitable zone. So I drew a cartoon. So I was debating this with some astronomers, and I said, okay, this is how you think of exosystems. Here's the star, and the further you get away from that star, the less energy you receive from that star. And so the hottest planet is the one closest to the star, coldest planet is furthest. This is the habitable zone. And this is a cartoon of our solar system, not to scale. But it doesn't work so simply. It's a bit like the difference between, in physics, if you use Newtonian physics, you can explain everything that's greater than an atom size. And then once you shrink down and look inside an atom, all the rules break down, everything goes crazy. That's how I would argue that planets, once you zoom in on them, their internal sort of geology and environmental chemistry means the rules don't apply so well on a smaller scale than when you conceptually look at a large scale. So if we go through our solar system, the surface of Mercury at night is one of the coldest places in the solar system, even though it's right by the sun. Mercury has almost no atmosphere, so at nighttime, it's barbarically cold. Venus is the average its average planet's surface temperature is the hottest in the solar system, but it's not the closest to the star. Then we go a bit further. Let's look at Earth. Perfectly habitable, right? Bang in the habitable zone. But the moon is also in the habitable zone. The moon is not habitable. You see humans on the moon wearing life-saving suits, right? It's not a nice place to be. Mars could have some water, briny, really salty, and this is consistent with it being in the habitable zone. But then most of our targets at the moment for extraterrestrial life are that we could have oceans of water on weird icy moons in the outer solar system. So if we work with the habitable zone definition, we completely ignore where most of the liquid water probably is in our solar system. So it's much more dynamic. So this, as a concept, is incredibly misleading. I think it's incredibly useful. It helps us filter. You don't want to be too close to a star because there's too much energy. But there's another factor here at play here. So Earth is habitable and Venus is not. So let's write this out. Let's try and work this out. How do we work out how Earth got habitable? Now the question is, how did Venus not become a habitable planet? So we can write Earth doesn't equal Venus, and this symbol just means does not equal. But we can't, if this was a simple equation, such as 1 doesn't equal 2, but we can't solve for Earth or Venus independently. We have to look at both planets because they're both they're dynamic systems. There are multiple variables at play. And this is because what we're looking at today is 4.6 billion years of happenings. Things have been happening for 4.5 billion years, and what we're doing is looking at right now. So it's like trying to work out. Imagine if you've never, ever, ever seen a foodstuff. Now, I was just in China in August. Some of the food that was served was, I couldn't comprehend even what it was. How am I going to make that? When you see a cake that comes out of an oven, when you look at the ingredients that go into a cake, they don't look anything like cake. And so we need to work out how this cake was made from the very beginning all the way through. And for Earth and Venus, this is 4.6 billion years of time. And so we know Earth's habitable. We're here, right? I think, therefore I am. Or I could be insane right now in a mental institution and be talking to the wall. Maybe I am. So Earth hasn't always been a cozy place. So this is at 4.6 billion years. This early period of Earth is referred to as the Hadean because it was like Hades. It was like hell. And through Earth's history, we've had some really dramatic changes. So let's think about growing up. This is like a baby. Can't look after itself. This is when the person reaches the age of 11 and thinks they're an adult. This is the goth phase. And then now this person is a respectable solicitor wearing a suit. And you might look at that solicitor and think, what a square. You don't know what they got up to at uni when they were a goth. And so we need to understand development of people to understand the person you're speaking with. Same way we have to do this with planets. But then there's also another factor. One thing that has changed over 4.6 billion years is that the input of energy is the sun. Now, we can draw this as a simple diagram. Right? On the y-axis here, we have time in billions of years in the past. This is roughly where some people think life began on Earth. This is the Cambrian explosion. And then big animals are here. And we're right at the end. And this red line charts the difference in the solar luminosity relative to now. So this is 100% solar luminosity, which is what we have today. If you go back to, say, 2.5 billion, the sun was 80% like as bright as it is now. And this has formed what's known as the faint young sun paradox. So Carl Sagan and Mullen put together a few calculations where they said this green line is Earth's surface temperature as a function of solar input for an atmosphere of 1 atmosphere with the rough chemistry we have now. And this dashed line is the freezing point of water. So if Earth's atmosphere was as it is now, until about 1.5 billion years ago, we wouldn't have had liquid water on the surface. We should have had ice. And so this means either there wasn't any liquid water, which is contrary to vast amounts of geological evidence, or there's something was different about the atmosphere that enabled us to maintain a temperature which meant liquid could be stable, water could be stable as a liquid. And so if you think about that, right, the sun wasn't as bright, right? We were receiving less energy from the sun. So was Venus. So would this lovely Goldilocks zone, this gray band of happiness and life, would that have been more around Venus? So no. Some people have investigated this, and a guy called Michael Way, who's in the United States, did some calculations and said, what about Venus here? So let's go like 2.9 billion years ago. What would the surface temperature of Venus have been with less input from the sun, this weaker sun? And then what he showed here, so this gives you temperature. On this side, on the top is Earth. So this is the ocean temperature, and this is the temperature on land. So these are not modeled, these are empirical. These are Earth's surface temperatures. And we get a large range, right? So here's like Siberia in winter, and then up here is like the Sahara in summer, for example. Scotland is just about 10 degrees all year. Pretty much, we don't really have a large temperature swing. 15 to 5 is about what we get. The ocean temperature's here, so you get some really hot water in the tropics. I'm guessing the North Sea must be around near this bottom bit here, because our students every May go and jump in the North Sea, and there is no way in hell I'm ever doing that. But they modeled actually that, now this is a model, of course it could be wrong, but it's interesting to see that it's conceivable that Venus could have had an ocean temperature around 20 degrees Celsius and a land temperature between minus 20 and plus 40, not too dissimilar to Earth today. This is very exciting. You think, wow. And then the title of their paper included, maybe Venus was the first habitable planet. And they went even further, and Venus has a tiny amount of topography. And they tried to calculate how much land mass Venus would have relative to ocean. And then they plotted Venus in gray against Earth. And it's not too dissimilar. But that meant that the press went crazy because it had the words habitable in first. And they converted this into this nice map of Venus now. This is Venus with oceans. Isn't it lovely? Doesn't have the same amount of cloud cover. So this is possible. And so this means trying to understand, did that happen is one question, or did it not happen? And if it did happen, why didn't it continue? The problem with, there was a meeting here, I think last year at the Geological Society called A Puzzle of Earth's Uninterrupted Habitability. It was awesome. Because when you think about the fact that Earth's habitable, that's interesting enough. We have life on Earth. But to have billions of years of uninterrupted occupation of a planet is just sensational. So we want to understand what factors control the environment in which life lives. So the habitable zone is completely misleading. Venus maybe was once habitable. Now, I've just basically completely poo-pooed the notion that distance from a star denotes habitability. And I'll stand by that. And so what else do we need to know? Well, the greenhouse effect. Right now, we're warming the planet by adding parts per million levels of CO2 to the atmosphere. Venus has 96% CO2 in the atmosphere. Earth, most of our CO2 is sequestered by life and chemical weathering, but this principle alone shows you that the environment, the atmosphere around a planet is hugely important. And so really, it's the pursuit of coziness. Right? Now, these are pictures of me wearing different clothes, and I am cozy in every single picture. But where I'm wearing shorts, this is Scotland, by the way. So it's either that I can just take it or that it was actually warm. Here's me in southern England walking the dog. Very nice, like wrapped up, but not too wrapped up. Here's me in Greenland in August. This is a Greenlandic summer. This is the outfit you wear in summer in Greenland. Now, the important point to note here is that my internal energy production is the same in all these pictures. Now, my clothes there represent an atmosphere. So imagine my skin is the surface, rocky surface of a planet. The clothes on the top insulate. Now, an atmosphere around a planet, all else equal, a bigger atmosphere means a hotter surface temperature. So if Earth today had an atmosphere the size of Venus, we wouldn't be a habitable planet. We'd be too hot. Maybe if you took the Venusian atmosphere and whacked it around Mars, Mars would be nice and warm and probably clement. So the question isn't just about where are you in the solar system. The question is about what's the medium around you. What is that atmosphere? Now, everything we know all life lives in the atmosphere and hydrosphere, really. Even in the rocks, deep life is still wet. Now, I'm grouping atmosphere and hydrosphere into one bag here and saying that envelope, that gassy, liquidy envelope, is one of the most important factors in denoting planet development. And so that's the target of a lot of what I do. And that stuff in the surface comes from the inside and can go back on the inside. And so that's where the volcanoes come into this story. So let's conceptualize this. Here's a photo of HL Tau. This is about 1 million-year-old solar system forming somewhere else in the universe. It's actually a photograph, basically. The dark bits here are where planets are forming by accumulation of dust. Now, 4.6 billion years is represented by this dashed line. And I would say, if we were to reduce this down to simple way of looking at it, either something happened or something didn't happen to Earth or Venus, which led to a completely dramatic change in their evolution. So Earth is very cozy, Venus is severely uncozy. So how do you make an atmosphere? Atmospheres are we take them for granted. When we see cartoons of planets, they're usually just the rock bit. So when the planet forms, it loses a lot of gas to space, especially helium and hydrogen. So helium is not heavy enough for our gravity to retain it. So whenever you see someone take some helium into their lungs and then speak with a funny low voice, the helium they're breathing out is going to go out to space and we lose it. One of the reasons why helium is very expensive. We can't hold on to it as a planet. But then over time, you get enough build-up. So this is showing you CO2 being removed by the oceans. This is showing water and ammonia being released by volcanoes. Doesn't matter what the gases are here. Just the point is that atmospheres don't just form. They're not static. They develop continually. And so there's another problem to face. Now, here's the 3 planets in our solar system that have atmospheres. Here's Venus, permanent cloud cover. Here's Earth, and here's Mars, very little cloud cover. But their atmospheres are hard to compare. So if we just look at the dominant elements in Earth's atmosphere, apart from argon, which we'll come to. So we can see that, Earth's not got a lot of CO2 in its atmosphere, lots of N2, and loads of O2. But the problem here is that we can't just look at the chemistry of the atmosphere and say, let's compare Earth to Venus, because of this. This is life. Right? This is a collection of organisms that dramatically affect life. And I love baby animals, which is why I'll always show pictures of cute animals. But these organisms aren't the ones of interest that dramatically changed our planet. These are the ones that benefited from that change. These are large-scale mammals, right? These need O2 gas. These guys. This is a very grim picture, I appreciate. Microbial life. Too small to see, but significant enough across this planet to have dramatically changed the air we breathe. And this is one way they did so. So here is the abundance of oxygen in Earth's atmosphere. Here is age in billions of years. This rise of oxygen here is known as the Great Oxidation Event. Earth's atmosphere went from being chemically reducing, where you might have methane stable as a happy gas, to oxidizing, which means there's O2 around. And O2 is one of the most unstable molecules. It likes to react with things. So right now, we have enough oxygen in the air to be almost combustible, which is why you get lots of forest fires in hot areas. There were periods when it got a bit higher, so the Carboniferous was a lot higher. Periods of Earth's history where there's been enough oxygen to have millipedes almost the length of this room, which is just horrible. Mosquitoes like flying dogs. Can you imagine that? So this is a problem. So we can't look at Earth's reactive gas chemistry to compare it to Mars and Venus, because we know that life has manipulated that. And that's really challenging. It's really annoying, actually, as well. And we can't just go back here and sample air. One of the main problems with air is it doesn't really precipitate rocks. Right? Think about it. The oceans precipitate rocks. And you study those rocks to study oceans and the history of the oceans and the history of Earth's climate. So but the oceans are only so old. But you can still have something. Air doesn't really make rock. But these guys now, on the other hand, these are the noble gases. And I'll refer to these as atmospheric spies. Now, I don't know why they were ever called noble. They're inert, but nobility is a good analog for them, because they don't mix with anyone else. They don't take part in all the regular things that people are getting up to. They just watch you. So 99.9% of, say, the argon, or the helium, or the krypton, or the xenon, or the neon, radon's a bit different, it's highly unstable. I suppose that's why they made it like a, so even though like the raging relative everyone has, like Father Ted type thing. But 99.9% of these are in the air, and they have been since Earth formed. So when planets form, we have a process called differentiation, which is a little bit like things segregating from one another, right? So all the gold went into the metal in the core, all the sodium and silicon went into the rock, and then the gases, these guys were just released, and they formed air. So although air doesn't preserve a rock, air potentially preserves some of Earth's earliest history. And the same true for Mars and Venus. So, the questions now arise, right? Did Earth and Venus begin with similar-sized atmospheres? Because they're roughly the same size planet, and so from what we've measured on the surface, the chemistries aren't dissimilar. So we sort of know the size of its metal core because it's the same stuff as Earth. But what about that gas bit? And that's the focus herein. And how has Earth's atmosphere changed through time? Equally, how has Venusian atmosphere changed through time? But how do you change an atmosphere? Volcanism. Volcanoes are not just really awesome and beautiful, magnificent, dangerous, deadly, and fertile grounds which humans live on. Volcanoes are also vents. And so here's the cartoon we saw earlier, and here's Torrealba in Costa Rica. And so if you go to a lot of volcanoes, there's this classic cartoon with steam coming out the top, or smoke. But it's not smoke, it's steam. It's mostly water a lot of the time. And so volcanoes are like pipes. They're just pumping gas out almost all the time. And that gas, some of it ends up precipitating out as oceans, some of it is carbonate that then life either sequests or that the oceans dissolve and precipitate carbon minerals, or they add more gas that just stays in the air. Now, here's a cartoon for Earth, right? This green bit is Earth's silicate mantle, and red here denotes magma. This dashed line is the depth in the crust at which we go from crusty crust to squidgy crust. And I'll give some examples of what I mean by this. And most volcanoes are fed from magma migrating through cracks. And we call these things dikes. And so rock fractures either by force of the magma chamber itself or by another means, such as an earthquake. And then the magma is able to utilize that crack and move upwards. Buoyancy-driven migration. But you need for buoyancy-driven migration to happen, you need a conduit for it to move through. So imagine if, for some random reason, everyone here gets really annoyed at me speaking, gets up and tries to leave, and they just push on that door will open. That's like a fracture, and then you'll go through it. If we all tried to leave, though, through here, we would walk into a wall and we wouldn't go anywhere. And sometimes that happens to magma inside a crust. It just stagnates and we get what's called a pluton. So this crusty crust, as I'm calling it, above this dashed line, I suppose the technical term would be a brittle ductile transition. So up here, rocks fracture like this. So this is a fault. This is just rocks breaking like plastic, brittle deformation. An analogy would be smashing of a plate. That's brittle. It breaks and it fractures. Now below this line, here's an example from, I've used this on purpose because it's from the Journal of the Geological Society of London. It was published 2016. And this is what it looks like in the field. So this, I suppose, is an analogy we give students on open days when we say, this is what people see. This is what a geologist sees. But what this shows you is these sediments here are faulted. They're fracturing, brittle. And this liquid rock, this magma, has utilized that fracture and formed a dike. Now, I don't know what happened, is whether tops cut off. This is in Argentina. This could have gone on to form a volcano, maybe not. But then below this, we have like Play-Doh, right? Like blue tack. Squishy, squidgy crust. It's not crusty. I don't know what you'd call it, though, if it's not crust. But we're not talking about the lithosphere here. We're actually talking about what's defined as Earth's crust. And this is an example of brittle deformation. So, sorry, ductile. Yes, thank you. So here, if you apply a force to these rocks, they fracture. Here, you apply a force to these rocks and they flow, they bend. They're accommodating stress in a way that means they bend. So an example would be if you had a yoga instructor in here and they pulled their leg up to their head, their leg would just go up. If you pulled my leg up to my head, you would rip my tendons. They would be brittle. Okay? And rocks change their behavior as a function of pressure and temperature. So this study came about because my friend Mike Heap and myself, Mike is a rock experimentalist. He deforms rocks for a living. So he's like engineering except for Earth. And we were talking about Venus, and I said to him, I was like, I wonder how rocks deform on Venus. And he was like, the same way they deform on Earth. I was like, yeah, of course, but Venus is really hot. So this shows you a profile through the atmosphere down to the surface. So Earth's average temperature at the rock, gas, or rock liquid interface is 4 degrees. Most of Earth's rock surface is on the bottom of the ocean floor. Surface to Venus is 460 Celsius. So I was like, that's cool. That means the geotherm starts at 460, and as you go deeper in the planet, it gets hotter. It's 460 degree difference in where the geotherms start. So I was like, maybe that affects the way the rock deforms, right? So what we did is we put some data together to try and investigate this. Now, this is a principle of how you would do an experiment like this. So engineers do this to look at building materials, and geologists do this to look at the building of volcanoes, for example. Like if you want to know the stability of a volcano, whether it's going to have a collapse, which could lead to an eruption, you need to know the material properties of the rock which build up that volcano. And fortunately, most surfaces in the solar system, including Earth, are made of basalt. Most volcanoes on Earth have a lot of basalt. We've measured 5 different times on the surface of Venus, and it was, unsurprisingly, it was basalt, just like the Moon, Mars, and Earth. And so you can experimentally, so this is a cartoon of an experimental apparatus where you have your sample, heaters on either side, and then you apply force. And you want to see how the rock deforms. So this would be how the data would come out. So here, this rock is deforming, 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 and then continual. So this is ductile. This rock is not snapping. This is what happens when it snaps. You get an instantaneous change in stress. So it's like, if you push your hands together and then do that, that's an earthquake, right? And so we went through the literature, because lots of people have worked on basalt, and because basalt's really ubiquitous to this planet, and a lot of people live near volcanoes, there's a lot of data. So we didn't do these experiments ourselves, I must add. And this is the data table that we published. So I'm not going to go into all of the data, but I'll show you what the data mean. So we plotted a diagram which tries to characterize the mode of deformation. And the colors here represent brittle and ductile, but I'll annotate this diagram because it's a bit confusing otherwise. But the important point before I annotate this is this red line is Earth's geothermal gradient. These lines are the Venusian geothermal gradients that we've had to infer. Now, we had to infer them because we don't have any heat flux measurements for the surface of Venus. But we do have data for the uranium, thorium, potassium abundance of the planet. And those 3 elements are the main energy sources internally. Those are what churn out energy. They give you heat. Now, we know that Venusian geotherm has to be positive, right? You don't get colder as you go deeper into a planet. You get hotter. But we don't know the slope. But that is actually not a problem. So when we overlay this diagram to show where these transitions occur, this is, on Earth, the brittle ductile transition can be as deep as 20 plus kilometers, sometimes 15 kilometers. On Venus, on the other hand, this is a very shallow layer of brittle crust. Think of it as a creme brulee, right? Really shatterable at the top, but then squidgy. And this is really cool, because we thought, imagine if Venus has a really malleable, deformable crust. What would that do? So on here shows you the average depth of primary magma chambers on Earth. And it's important to note here that these are below where the brittle ductile transition happens on Venus. So the top of Venus should be quite rigid, snappable, and that's consistent with data. If you look at the radar images, Venus does have fractures on its top, on its surface. But just like you can shatter the top of a creme brulee, that doesn't mean that most of that creme brulee is brittle. Right? We know it's not brittle. So the first thing we thought about was these maps here show you topography for Earth and Venus. And as in the introduction was mentioned, Venus is not a disk-world planet, but it's definitely not got the same topography as Earth. So Earth has a bimodal distribution of topography which reflect ocean basins and continental crust. The way these plots are made is that you take the planet's size and shape and you make it a perfect sphere, or you make it flat, and then you look at anything above and below that point. So this isn't relative to sea level elevation. This is relative to a perfectly smooth body of the same geometry as the planet. So Earth's geometry, we know it's not round, it's spinning, and it's elongated. Venus is spinning so slow, it's almost a perfect sphere. But so when you make the geometry of Venus a perfect sphere, and then you note what's above and below that point, and we set that as 0. And Venus, most of it's kind of, it's orange, covered in clouds and flat. So think of Venus as the Netherlands if it were warm. And so what we said was, this is cool. Maybe this means this is why it's quite flat, because, we know if you build on unstable ground or ground that can't support something, then you topple and you fall over. And if it's hot enough, you can flow. So that was the first thing we thought of. And then we went back to volcanoes and thought, what about volcanoes? How do you make a volcano through ductile crust? And so we said Venus is too hot for tectonics, but we weren't the first to say this, and I'm not going to focus on tectonics for this talk. But we did say maybe Venus is too hot to have lots of volcanoes like Earth does, because the squidgy crust on Venus is up to a much shallower level, and the crusty crust is very thin. So these magma chambers will find it hard, or harder, to find a mechanism to transport them to the surface, because we need these fractures. And we said, okay, that's an idea, but you're never going to get that through peer review in the scientific world, and you have to find further evidence in support of your notion. So this is when we turned to geochemistry. And fortunately, missions like this in the 70s, so the Cold War was frightening and bad, but for space exploration, the Cold War was awesome. We went all over the place. People were just sending missions regularly. It was fantastic. It was a heyday. And so this is a Soviet lander that went to Venus, landed on the surface, took photos even, and measured the chemistry of its atmosphere, including those noble gases. This is the USA's version, NASA's version, that also measured noble gases. So we had 3 or 4 different measurements that all corroborated. So all the data made sense. They all gave the same answer. So we sort of trust the data to some degree. And we had the same for Mars, and we have lots for Earth, of course. Now, I've put this slide in here because I don't want to just jump into the word isotope and confuse anyone, because I realize when I teach now that isotopes are abstract. So what an isotope is an element with a different number of neutrons but the same number of protons. So argon, which is what we're going to focus on now, has 3 isotopes of interest today, right? We list isotopes with a number followed by the element symbol. So argon-36 and argon-38 are what we call primordial. The amount of argon-36 and 38 on Earth has been the same pretty much since Earth formed. Argon-40, on the other hand, is the product of radioactive decay. And it's the decay of potassium. So potassium is radioactive, right? And it decays to form argon-40. And so that means the amount of 38 and 36 shouldn't change through time, but the amount of 40 argon in the air should change through time, depending on how much argon-40 we're pumping into the air from the decay of potassium. And this is really important because, as I said, most of the argon, 38 and 36, 99.9% of it has been in the air since the Earth formed. But when Earth differentiated and all the gold went in the core, the potassium was in the rock. And that potassium breaks down to argon that's different from the argon that was in the air. So that's the key point. And so the amount of argon-40 in the air has to reflect the amount of gas that's come out of the planet. Because the argon-40, initially, there wasn't any in the air. It was all potassium and rock. Okay? And this is a plot because we need to know the potassium inventories. This shows you a lovely illustration, I think, of Mercury, Venus, Earth, Moon, Mars. Now, the important point here is this is the potassium-thorium ratio. So this was used to talk about heat generation in planets. But I find the uncertainties are quite large. But Earth and Venus within error, potentially have the same amount of potassium, which makes sense for two planets of the same size that formed in the same solar system that formed at a very similar distance from the star. So none of this is groundbreaking. They should be the same. And it's really nice when you think they should be, then you look at data, and within uncertainty, they are. So we'll move forward with this. So Earth and Venus should have had the same amount of, since they formed, the same amount of argon-40 produced inside them, because they have the same amount of potassium. And then the first check we did was looking at the non-radioactive isotopes to see if they started off with the same sort of chemistry. And Venus and Earth, so Mars has lost a lot of its atmosphere because its gravity is a third of Earth and Venus. It finds it hard to hang on to its gas. And the sun is an evil being. The sun is just constantly trying to bombard planets and strip them of their atmospheres. It's quite a horrible thing. And so, but Earth and Venus within uncertainty seemed like they had the similar sort of non-radioactive gas chemistry. So that means over time, the amount of 40 argon in the air of these planets should reflect the amount of 40 argon the planets have expelled from the rocks. So the present day ratios are the same as the sun. So Earth and Venus started out with the same position chemically. And that means they're initially, when they first formed and developed an atmosphere, the amount of 40 argon in the air was 0 because it was all potassium in rock. And therefore, increasing argon-40 in the air is achieved by what we call degassing, so a planet expelling gas. And if we plot these data as a function of distance from star, so here's astronomical units, this is where Venus sits, this is Earth, and this is Mars. And we'll go through this and explain what these data mean. So we said Mars has lost a lot of 36 argon, and so you can't take its 40-36 ratio to mean anything about degassing. It probably means more about atmospheric loss. So with a ratio here, if you take away lots of 36, you increase this ratio. So we don't consider Mars herein. But the fun thing here is that Earth and Venus are different, and Earth has considerably more of this 40 argon in the air. And I'll show a cartoon to explain how we get argon out of a rock and into the air. So this is a rock, very simple rock. It's like a peridotite. We have clinopyroxene, and we have olivine. If we had potassium in this system, most of it would be in clinopyroxene. And so this is what the mantle is pretty much made of. And so all that potassium is going to break down to form argon. And once it forms argon, it's become noble. It no longer plays friendly with the surrounding atoms. It doesn't form bonds with them. And so it slowly just leaves the party. That's called diffusion. And so the things that keep elements in minerals is bonds. And if you have a charge of nothing, which the noble gases do, which means they don't like to form bonds. So imagine if everyone holds hands. And as we hold hands, I all of a sudden get appointed a lord. And I think I'm now noble. I let go of your hands. I can then just slowly creep through you. And if it's depending on the temperature, depends on how quickly I can run away. And then fluids move through a rock. They can transport some of this argon away. And if a melt moves through a rock, it can transport some of this argon away. Now on Earth, we found reservoirs of water in crust that are like 2 billion years old. So it's not a given that argon produced inside of a rock, inside of the crust or the mantle, will actually leave. Most of it doesn't leave. You need something to come through and transport it out. Like, you see people at airports. People don't really leave airports unless they're on an aeroplane, right? The airplane, in this case, that gets people from A to B is either, say, fluid, so let's think of water percolating through rocks, or liquid rock, melt, volcanism. And we calculated and argued that diffusion on Venus is restricted if melts aren't moving through these rocks. If there's less volcanism, so even if the melts form, they can have this 40 argon. If they crystallize, it just stays in the rock. It's not going to be in minerals, but it can just sit between grain boundaries quite happily and do nothing. And so this would mean that magmatism on Venus is dominantly intrusive relative to Earth. And so the chemistry data is empirical. Those were measurements from Venus and Earth. The experimental rock deformation data are confirmed. They're experiments. They've been rerun. They work. The bit of this that's most tetchy and least defendable, I suppose would be the word, is the diffusion experiments. And so I'm very grateful. The Royal Society have thought this is also interesting enough, and they're supporting us financially to do some of these experiments. So this is ongoing to some degree, but we have published our results. And so if we take this all together and try and see what it means for the atmospheric development of these planets, if we count the number of stratovolcanoes, so this is just looking at images and counting volcanoes, relative to the age of the rocks. So most of Earth's oceanic crust, for example, is less than 100 million years old. And we don't really have a good handle on the age of the Venusian surface. But most people think less than 700 million. And so Venus has produced less volcanoes in more time than Earth. So Earth has produced about an order of magnitude more volcanoes than Venus as a frequency of volcanic production. And we say maybe that's evidence that Earth really is producing more volcanism. And if we couple that with the argon story and another story that I won't present today, which is to do with nitrogen, both of these different approaches give us the data that suggests Earth has degassed 3 times more than Venus. And that's really important because, so we argue that Venus is so hot that volcanism is inhibited. It's not prohibited. You do have volcanoes on Venus. And the chemistry data suggests 3 times less gas release from Venus than Earth. And one of the important gases that we haven't talked about today but would be implicit in this is water. Now, if you took all the oceans on Earth and put them back into the rocks throughout the whole mantle, nothing would happen. The mantle is what we would say undersaturated. So it's a bit like when you use a dry towel on a wet body, the towel absorbs the water away. Earth's mantle is effectively below the point which it can still store water. So a lot of water on Earth's surface may well have come out of volcanoes. And if there's been less volcanism on Venus, maybe Venus is a planet that has more water inside it than Earth. That's conceivable. And so when we look at these exoplanets, how do we know if they've had a history like Earth or Venus? And I like to finish with unknowns rather than just trying to act like I know the answers to lots of things. So what could have constituted this? Well, this is Earth's atmospheric history, and I've shown here the Carnegie Institution of Washington, who supported some of my work, as well as NERC. And this line is the most interesting. So this shows you how Earth's carbon dioxide in the atmosphere was sucked down because of weathering and life. But we don't actually know how much carbon dioxide Earth started out with. We don't even know how much carbon the Earth system has. And if you're interested in carbon, the Deep Carbon Observatory, an amazing organization who are just trying to understand absolutely everything about carbon. So if we ignore these reactive gases and look at the noble gases again, they give us some telling insights. Forget the CO2, forget the water and N2. These are the primordial isotopes of neon and argon. Venus has about 2 orders of magnitude more of them than Earth. So that means if we use these isotopes to see through life, see through chemistry, Venus started out with a bigger atmosphere than Earth. Now, Venus is a bit smaller than Earth. Why would a smaller planet have a bigger atmosphere? Coming back to this, something happened, something didn't happen. Maybe, tentatively, this relies not in Earth's internal generation, but maybe Earth took too much of a beating. Now, Earth's not alone. We have a moon. Venus has no moon. And our moon formed in arguably one of the most violent things that's ever happened to Earth. This is an artist's impression of this event. 2 planets collided, and the debris that was flung out from this high-energy collision gave us a moon. But importantly, the amount of energy in an event like this means a lot of gases can reach what we call escape velocity. And you don't need a big impact. Every meteorite that hits Earth removes some of our air. Right? Every single one. Small ones, big ones. I say slow and fast, but we're talking 10 meters a second versus 60 meters a second. Pretty fast. And so when something hits and you lose atmosphere, maybe, just maybe, Earth got beaten into life. Right? Earth received more exogenic rock. after it had formed. Maybe it was a single event like the moon, maybe it was multiple events. But we can answer that question. Now, I can't do this alone. So Laurie Glaze, who's at NASA's Goddard, put this amazing figure together, which is a puzzle of the solar system. And she's proposing to return to Venus, which is the missing piece of this puzzle. And if we were to have a full suite of analyses of these nobles from Venus, we can actually answer that question as to whether or not Venus really started out with a bigger atmosphere, and whether or not we can explain how Earth became habitable and why Venus did not, and then we can move forward to understanding other planets. So in conclusion, I'll just say that we can further constrain how volcanism and tectonics have changed the nature of the air we breathe. And optimistically, I'd like to say we live in exciting times, and I think we're going to have more answers, more insight as time goes on. And thank you very much.
Thank you so much, Sammy, for that fascinating talk. We do have about 10 minutes for questions, if anyone would like to raise their hand. Before you ask your question, please wait for someone to come around and give you a microphone. That's just so that the people who are watching online and the recording can pick you up as well as us. So I will open it up to anyone who'd like to ask something. Yes.
Yeah, it's
Yes,
coming.
it's coming around.
I was already making notes about the nitrogen question, which you don't want to go into, so I won't go into that. Is it credible that by doing something like an aerobraking maneuver with the satellite, you'll be able to sample enough of the Venus atmosphere to get a good measure on the noble gas compositions that you're interested in? Without actually trying to land on the surface, which is a bit of an engineering challenge.
Yeah, so what you're referring to, if I'm right, is where instead of going into the atmosphere proper, you go in and you come out. You sort of skim it.
Lower your apogee, not apogee, upper side. You lower your furthest away from the planet part of the orbit by losing energy in the atmosphere. It's used routinely for putting probes into orbit around Mars, but it's a bit heavy.
Yeah, see, the two things here. One, to measure the atmospheric chemistry as I proposed, you don't need to, you land eventually, but you don't need to worry about the landing part. You just need to fall through the atmosphere. But two, there is a depth in the atmosphere where you need to be below. It's for what we call homogenization depth. I don't know what that depth is in numbers, so I don't know engineering-wise if we were able, because Venus has a lot of gravity, and so it's really hard to escape. And so I don't know how deep you'd have to go. I mean, so I would say they probably have that information at NASA and at Roscosmos, so I would have to defer. If you want, email me and I can try and find the answer. This guy's had his hand up a couple of times as well.
Two questions, really, but they're very, very short.
Okay.
Have volcanoes actually been seen on Venus? I've heard it speculated that Venus must have had volcanoes millions of years ago, but has anybody, or have they actually been detected now?
Yes.
They have?
Yes. There's there's a few lines of evidence, but one is infrared, where there's an area that's been seen a few times and it's got a constant temperature, and then they looked at it again and it was a couple of 100 degrees warmer in a shape that looked like a flow. And that could be best explained by an eruption. The other bit of evidence is the sulfurous, part of the clouds of sulfuric acid, which is unstable in the atmosphere, and so it has to be replenished. And so the best way of doing that is volcanic. Also, geomorphologically, we've seen things that are perfect cartoons of volcanoes on Venus.
Thank you. And the other question is, I hope you don't mind me asking this. I read somewhere that if an astronaut was standing on Venus and he leapt off a mountain without a parachute, the ocean would be deep, or the air would be thick enough. If he just spread his arms and legs out, he would just drift down without. Is that rubbish, or is that, or would you say that that's got any basis of fact with your knowledge of it?
It makes sense, right? Because the surface of Venus, the amount of pressure there is the same as being 1,000 meters below the ocean.
and its gravity is roughly the same as what
Yeah,
ours
so I
is.
suppose, yeah, probably would.
I
don't know if I'd want to do that experiment
myself.
I'd pay someone else to do it. So yeah, I'm not sure. I mean,
you couldn't do it on Earth because you
could if you jumped from 1,000 meters below. You jump in the ocean,
No, I mean,
right?
yeah.
You don't drop like a lead balloon. So maybe, yeah. I mean, I don't know.
Sorry, I had to ask.
I'm going to have to look that up. I want to know. Maybe then you could fly, right? Would you need big wings if you just flapped with ironing boards on both arms, right? If it's that thick.
I mean, ignoring slight inconveniences like 460 degrees centigrade, where you
Slightly
get
inconvenient, I agree. Yeah. 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 Just go here.
Thank you for a very interesting talk. You mentioned how the atmosphere has changed since the two planets were emerged from the original formation of the solar system. Now, the sun is approaching halfway through its life, and during that time, it has heated up. In fact, it hasn't reached its maximum temperature yet. And we know that from investigations taking place on Mars, that they think there's water there, and they think there may be microbial life in the strata somewhere. I just wonder, during the next few million years, is it possible for Mars to recreate an atmosphere to produce life?
Well, Mars has got a very thin atmosphere for one, but you do raise a point. Some people are trying to calculate now. Mars will one day be more clement because the sun is getting brighter. Earth will become uninhabitable. The sun will actually eat us at some point. But yeah, Mars could easily become a more habitable. I mean, it's already at the moment. The subsurface of Mars, once you go below the surface, the radiation levels will drop off. If there's a groundwater system, it could be habitable right now. And it might be ironic that when heating it up might actually disturb the environment. So it's still yet to be seen whether or not Mars is habitable or not.
And whether it happens before we have a collision with Andromeda.
That's way in the future.
One of your charts showed how the temperature increases as you move towards the core of a planet. What's the thickness of the surface zone which sees the opposite effect? So a wine cellar in Champagne, 30 metres underground is nice and cool. At what point does it start getting hotter again?
Well, it depends on where you are on the planet. So in Costa Rica and the Azores, so in the Azores is a famous way of cooking where they dig a hole 2 meters deep and they put some food wrapped up in it and leave it for 5 hours to cook. And it's 70, 80 degrees. If you're somewhere like the Canadian Shield, which is a super thick crust, then you'll dig and it's cold for a long time. So there is no specific guaranteed depth. It depends on the heat flow at the particular place that you're digging. And Earth has an amazingly dynamic surface with various different lights. So look at Iceland, right? They have a lot of geothermal power because it's so hot, so close to the surface. And so it depends where you are on the planet. And we really don't have a handle for the heat flux anywhere on Venus. So that would be amazing to know. But as I say, it depends geographically where you are on this planet. And so think about the distance from here to Iceland, right? It's not big, but the heat flux at Iceland is far greater than it is in the UK. Yeah.
Do you think the lack of a convective mantle system is also a factor in the lower degassing in Venus?
Yeah, I think the funny thing about planets, right, is everything's connected. So the surface temperature on Venus is so hot that the heat flux will have to be lower than it is on Earth. And that has a knock-on effect. So the best way to get things moving is make a gradient, chemically or thermally. So Earth has a super cold surface and a hot interior. That sort of drives some convection. And so, yes, convective rigor causes things to move quicker. And sometimes if you take something from deep in Earth, you move it up quickly, it doesn't lose its heat, but its pressure drops, and that causes melting. We call that adiabatic melting. And so if Venus has more sluggish convection, then it will also have less adiabatic melting. And so I suppose, you know, the weather on Venus actually could shut the mantle down. Imagine that's in terms of interconnectivity. But the real interest to me is what came first? You know, did the planet itself have such a sluggish amount of volcanism that it allowed itself to hit the runaway greenhouse? Or was it the other way around? Was it so hot that that shut down what was... Because the surface of Venus, unlike Mars, is very young. It doesn't have many impact craters on it. So we don't know the Venusian deep time history. Venus could have once been great and habitable and lovely, and something happened 3 billion years ago. It changed, and now its young surface doesn't preserve that to us through radar. So this is why I would suggest a full noble gas analysis of the atmosphere, as long as more landers as well. You know, Venus is the size of Earth, and we have like 4 or 5 pictures, which are, imagine if someone took a picture of the floor with their foot for scale. That's what we have from a planet the same size of Earth. And geologically speaking, it's a puzzle that's too difficult for anyone to solve with such a data set.
Thinking of the effect of the moon on Earth, the moon was once much closer to the Earth. Yeah. That would have increased its gravitational effect. Could that have had an effect on stimulating some movement within the crust, which would then have degassed more, etc., etc.? Would that have an effect, whereas Venus not having a moon would have lacked that effect?
It's a very cool question. Right? So we know that even something as, you know, Earth's huge, Earth's powerful, rocks are amazing, but even something like melting of a glacier can trigger volcanism through pressure release. So I've never thought about it in how it would drag melts, because the moon, the tides would have been barbaric 3 billion years ago, like tsunamis every month. So, day, actually, yeah. So we could have easily had a situation where that pull could have affected melts. I wouldn't mind, this is recorded, so some of these questions that I haven't been able to answer, in fact, you suggested we put these in the magazine. You should write down these questions and answer them in more depth, and if Geosoc would put that then in the magazine, I think that would be useful. Because some of these are really fun questions, and I'm totally going to Google them and look into this. And so I think it'd be a good idea to then put this out there for anyone else who thought, that was a good question, what is the answer?
Well, if there are any more questions, is there just one more down here? Why not?
It's maybe a little bit trite, but could the fact that you've not got the craters on Venus be due to the fact it's got a squidgy crust?
We didn't go there. I don't necessarily think so, because that top bit's so brittle, right? And it does preserve fractures. So we see fractures. So if you can preserve a fault, like the San Andreas expression we see from the air, then you'd preserve a crater, right? So we let that one go. I mean, we came up with the idea for this after a wedding in Bristol. My friend lives in Strasbourg, and I'm in Scotland, right? So the next morning after a volcanology wedding in Bristol, we were in a cafe, and I liked this guy I worked with. We'd lived together for years. We've been best friends for like 7 years. And we're like, let's find a way of working together. And we started talking about the surface of Venus being smooth, and we said, but then it doesn't seem hot enough that it could completely relax a crater.
But it could, if it's squidgy underneath, it could come up and seal it.
That is possible. But I suppose it's worth investigating further. But it's really hard to get rock to not just move up, but move up and melt and then infill. Energetically, just because of the way it deforms, is hard to sell. There must be a way of calculating that, though. Right?
Would the length of day impact on that?
I'm not sure if it would impact on that. You mean on melt migration?
It's a long time to turn around.
It does, doesn't it? Over a year.
So the temperature facing the surface, facing the sun, it never gets a chance to relax.
Yeah, but then equally the temperature of the night doesn't drop on Venus. So I don't know if anyone's ever been somewhere really humid. I lived in Washington, D.C. for 2 years. And in summer, it's awful because the nighttime temperature doesn't drop. And Venus has got such an intense greenhouse that whether you're in day or night, North Pole or equator, it's the same temperature. It's a really weird world. And this is what I mean when you look at exoplanets, just because they're the same sort of size, similar distance from, how do you know it's not a Venus? I really need to know. Right? So no, I'm not being critical for the sake of critical. I really want to know. And yeah, hopefully one day I'll get there.
We should probably wrap it up there as we've gone slightly over. I feel like we've just started an impromptu research. Thank you very much.
What time's the next one?
6.
Okay.
Yeah. I feel like it could have gone on for
Yeah. What do we do
another
till
half hour
6?
of questioning. Actually, if you don't mind, I'd love to grab 5-10 minutes to record a podcast, if that's all right.
Yeah.
So more
A cup of tea?
but yeah, I can
Cup of tea first?
grab a cup of tea. That was brilliant.
Thank you so much. Great question. Someone's phone's on the
That's
floor.
me, yes, I left it behind. Thanks.
Hello.
I'll get your email address off you when it's more convenient.
Yeah, sure. I can write it down now if you want.
Oh, right, okay. Hang on.
Pen right here.
Pen, yeah. Mm-hmm.